Hello students, subscribers, viewers, and future engineers. I'll divide Algebra 2 into maybe 3 parts or 4 parts so that it will only take uh, maybe more than 10 minutes to discuss or for the size or the length of this video. So I will discuss permutations and combinations in this video, and we define permutations as a definite arrangement of all parts of a set of objects. So here, repetition is not allowed and order matters. And before we proceed, let's have this fundamental principle of counting, which is very important in determining the number of ways that events can occur. Number of different ways that events can occur. So this is the fundamental principle of counting. If one event can occur in n different ways, and after it has occurred in any one of these ways, a second event can occur in n different ways, then the number of ways the two events can occur is simply the product mn different ways. This pattern can be extended if there are more than two events in the situation. So it means that there may be 3, 4, 5, or many events. Then this pattern, this fundamental principle of counting can be applied. So for instance, you have two brands of pants and three brands of shirts, three different brands of shirts. So the question is, in how many ways can you wear a pant and a shirt? In how many different ways can you wear a pant and a shirt? So if your pants are, let us say, Levi's and Lee as brands, and your shirts are Giordano, Bench, and Hanes, then we draw horizontal bars. Then there are two ways to assign uh, pant, because you have two brands of pants in the first event, and in the second event, because you have three different shirts, so 3. Then from the fundamental principle of counting, 2 times 3 is 6. In particular, these 6 different ways of wearing a pant and a shirt would be Levi's and Giordano, Levi's and Bench, Levi's and Hanes. So that's already 3. Then Lee and Giordano, 4th. Lee and Hanes, 5th. Lee and Bench, so 6. Those are the 6 different ways where you can wear a pant and a shirt. So I hope that's clear, the fundamental principle of counting. So let's consider the numbers 1, 2, and 3. If they are arranged all at a time, there will be 6 different permutations taken all at a time. Taken the 3 digits all, or 3 numbers all at a time. So if we write them, these are 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 2, 3, 1, 2, and 3, 2, 1. So 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. So these are the different permutations or arrangements if all the digits are taken all at a time. The 3 digits are taken all at a time. Then if we apply the fundamental principle of counting, we draw 3 horizontal bars. In the first bar, there are 3 different digits available. We can assign 3 different ways in the first position. 3 different ways, but only one digit is assigned. It's either 1, 2, or 3. So that's the meaning. So 3. After assigning 3 in the first position, there will be 2 digits left. Then there are 2 ways to assign the second position, the remaining 2 digits. Then after assigning the second position by one digit, there will be one digit left. So 3 times 2 times 1 is equal to 6. And these are the details of those 6 different arrangements. So I use this horizontal bar method in answering that, and of course the fundamental principle of counting. So that's a method of counting by drawing horizontal bars as the position of objects to be arranged and the corresponding number of ways of placing an object on that bar. So by the fundamental principle of counting, the number of arrangements can be found. So let's have this theorem 1. The number of permutations of n distinct objects taken all at a time is n factorial. So n factorial, if you're familiar with that from your advanced math or from your experience. So for instance, if you have 3 factorial, for example, 3 times 2 times 1, that's the meaning of that. 3 factorial is 6. So you try 4 factorial, that's 4 times 3 times 2 times 1. 10 factorial is the product from 10 up to 1. So 10 times 9 times 8 times 7 times 6 factorial. You may stop at 6 factorial, but the meaning of 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. So it is still n factorial or 10 factorial in general. So let's prove this theorem. So NPN is n factorial, or just put capital N, that's the total that's the number of permutations. So I draw supposedly n bars because there are n objects, distinct objects to be arranged. So this is the first, second, third, then dot dot dot, this is the art next to the art term, then until we reach the last bar, which is before that there will be one object left. So therefore, in the first bar, since there are n distinct objects, we can assign n different ways in this position. In the second, after assigning one object there will be n minus 1 left. So there will be n minus 1 ways to assign this second position. So arrangement in a row, straight line. Then in this next, n minus 2, because we have already assigned one here, and we can assign n minus 2 different ways for this third position until we reach this art position. So that's the first, that's the second, that's the third. So this is the art position. So what would be the number of ways we can assign an object in this position? Let's study the number of ways we assign to the first, second, and third, especially the third. So if this is the third position, if this happens to be n minus 3, then it's obvious. But this is only n minus 2, which is quantity 3 minus 1. So therefore, the art position, let's check also the second position. We assigned the number of ways we can assign an object here is n minus 1, which is, in general, n minus quantity 2 minus 1. So that's n minus 1. The third position, n minus quantity 3, or third, minus 1. So that's why n minus 2. Therefore, the art position, in general, this is, we can assign an object here in n minus quantity r minus 1. So that's the last. So n minus quantity r minus 1. So if we simplify this, this is n minus r plus 1. And since this is decreasing by 1, n minus r plus 1, the next here should be n minus r plus 1 minus 1. So n minus r until we reach the last. Of course, in the last position, because all objects are to be arranged, all different and distinct objects will be arranged, then there will be one object left. So there's only one way to assign the last position. So by the definition of n factorial, it is the product of n minus 1, n minus 2, n minus 3, and so on and so forth until the first. So this is like 10. If n is 10, 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So therefore, that is obviously n factorial. So npn is n factorial. So for the second theorem, the number of permutations of n distinct objects taken r at a time, where r is less than n, of course, is npr equals n factorial divided by n minus r factorial. So let's also prove this theorem. Let's go back to this, but this time we only arrange r objects from n. We only take, or we only arrange r objects from n distinct objects. So I'll draw bars. How many bars? R bars. This is the art bar. This is the first. So because there are n distinct objects, we can assign n different objects here. We can assign in n different ways and one object in this position. In the second position, there will be n minus 1 objects left. So there will be n minus 1 ways to assign an object in that position. Then 2 objects have been positioned in place. So there will be n minus 2 objects left for the next position, for the third. So there will be n minus 2 ways to assign an object here. This is the art, and based from our results here, for the art bar, then there will be n minus quantity r minus 1 ways to assign an object here. So if we simplify this, this is n minus r plus 1. The next should be n minus r. But this will not change if we multiply quantity n minus r factorial and divide by the same thing n minus r factorial, right? So what's the meaning of the numerator? What's the equivalent of the numerator? The numerator is simply n factorial. Why? It's like if n is 10, 10 times 9 times 8 times 7 times 6, let us say times 5, and times 4 factorial. If you expand 4 factorial further, it is 4 times 3 times 2 times 1. So therefore, this is n factorial, the numerator. So that's why divided by, we have n minus r factorial in the denominator. So that's the formula for the number of permutations of n things taken r at a time. So you may practice, try evaluating 5 P2, 5 shift times 2 in your calculator. So that should be equal to 20. 5 shift times 2. So that's really 20. Then let's go back to this. Digits 1, 2, 3, if arrange, or if arrange 2 at a time, then there will be 3P2 ways to arrange them, taken 2 at a time. And these are specifically, so 6, 3 factorial over quantity 3 minus 2 factorial is 6, 3 factorial over 1 factorial. By the way, 0 factorial is also 1. We can prove that beginning with n minus or n factorial, then expand it as n times n minus 1 factorial. So 3p2 is 6, and these 6 are 12, 21, 13, 31, 23, 32. So 12, 21, 13, 31, 23, 32. So there are 6 permutations of the digits, or the numbers 1, 2, 3 taken 2 at a time. So I hope it's clear and the formula is also clear. You can use the formula if you want. It will give us 6. Then another arrangement, permutations of n things of which some things are identical of or taken all at a time. So this is the number of ways of arranging, for example, words where some of the letters, of course, are identical, like Mississippi. There are so many uh, letters there which are identical. Arranging appetite, engineer, so words with identical letters, or arranging objects in which some things are identical, taken all at a time. So the formula is n factorial over quantity r1 factorial, r2 factorial, dot, 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 where r is the identical objects of the first kind, or yes, of the first kind. R1, R sub 2 is R2 things that are R2 things are identical of the second kind. If there is another kind, then that will extend to R3 factorial, and so on and so forth, depending on the number of identical things. Then we have permutations by groups. The group arranged in a row, the number of groups can be arranged in G factorial ways by principle. So, for example, there are G groups. So, the number of ways we can arrange them is G factorial, where G is the number of groups. Then, because let us say group 1 has M1 members, the members within the group can be arranged further in M1 factorial ways, where M1 is the number of members in that group, just like N factorial in the group. M2 is the number of members in group 2, then the members of group 2 can be arranged within the group in M2 factorial ways. If there is group 3, then times M3 factorial, group 4, M4 factorial, and so on and so forth, depending on the number of groups. So G is number of groups, M1 number of members in group 1, M2 number of members in group 2, and so on and so forth. Next, circular permutations. So let's have the objects, distinct objects arranged in circular manner. 1, 2, 3, 4, 5, and so on and so forth until the last. So this time, the arrangement is different if arranged in a row or horizontal line, or not necessarily horizontal line, like smiley face, concave upward arrangement. So the first and the last appear as one object. Because of that, it's like there will be n minus 1 objects to be arranged in a manner that is not perfect square, circle. So it's like this. So they are arranged, the n minus 1 objects are arranged in this manner. It's not n anymore. It's not a perfect circle anymore. So therefore, the idea is the number of permutations, circular permutations of n distinct objects arranged around a circle would be n minus 1 factorial, because of the fact that the first and the last are adjacent besides each other. Just it's different if this is the first and this is the last. That's why for that arrangement, there will be n factorial ways. But because the first and the last appear to be 1, let's just consider that as one object, so that there will be n minus 1 objects left, and this would be the arrangement. It's no longer perfect circle, which is equivalent to this. So I hope you get the idea. So permutations n minus 1 factorial. Then circular permutations. Some things are identical, taken all at a time. For permutations in a row, n factorial over r1 factorial, r2 factorial, if you can recall the formula. Here, because this is circular permutations, it's the same, except in the numerator, it's no longer n factorial, but rather n minus 1 factorial. Then we have r1 factorial, r2 factorial, and so on. Then how about combinations? We define combinations as an arrangement without a specific order. Repetition is not allowed again. So recall the numbers 1, 2, 3, there will only be one combination taken all at a time. So that's 1, 2, 3 only. If you have 2, 1, 3, 3, 2, 1, 3, 2, 3, 1, 2, 1, 3, 3, 1, 2, 3, 2, 1, we use the same digits. So that's why there's only one combination. So that's the reason. So it is NCN equals 1. So for example, 5C5, that's 1. 4C4, it's 1. 3C3 is 1. So use that formula, the 3C3. That is equal to 1. There is really one combination. Then, the numbers 1, 2, 3 can be arranged in 3 different combinations taken 2 at a time. What are those? 12, 13, and 23. So, this is just one combination. In permutations, we can have 21. In permutations, 13 can be arranged 1, 3, can be also arranged as 3, 1. But here, because the digits 1 and 2 are used in this 2-digit number, we have the same combination, 1 and 2. 1 and 3, same combination, 2 and 3, same combination. So therefore, what's the formula for NCR? So we observe that the number of permutations is greater than the number of combinations by this formula here. Remember that if the number of combinations of 3 different digits taken 2 at a time is only 3, in permutations it was 6, because in permutations these 2 different digits can still be arranged in 2 factorial ways. They can interchange position. That's why NPR is NCR times R factorial. So that 2 there is 2 factorial, and 2 factorial is 2. In permutations, we have 12 and 2, 1. So that's why 12 can still be arranged in 2 factorial ways. So therefore, the formula for NCR is NPR, which is n factorial over n quantity n minus r factorial divided by r factorial. So that's it. NCR is n factorial over quantity n minus r factorial times r factorial. So in this case, evaluate 3 combination 2. So in your calculator, type 3, then shift, divide 2, and it is 3. The total number of combinations of n things taken 1 at a time, 2 at a time, 3 at a time, ... or all at a time is 2 to the n minus 1. That 2 to the n minus 1 is the same as combinations of n things taken 1 at a time plus combinations of n things taken 2 at a time plus combination of n things taken 3 at a time plus that combination of n things taken r at a time plus ... until you reach combination of n things taken all at a time. That's 2 to the n minus 1. So to illustrate, let's have 4C1 plus 4C2 plus 4C3 plus 4C4. That's 2 to the 4 minus 1. So 16 minus 1 is 15. You also evaluate 4C1, then plus 4C2 plus 4C3 plus 4C4. you evaluate this individually and you will notice that it is also equal to 15. So that's it for this video. It's quite long now, and wait for the continuation of this video.